Trend analysis, using time series, plot, and box plot. Let's start by understanding trend analysis. Trend analysis is about evaluating data over time to identify whether things are increasing, decreasing, or showing repeating patterns or shifts. The goal is to detect the underlying direction or long-term changes in how a process is performing. This helps us decide if we need to take corrective action or sustain improvements. A key tool for this kind of analysis is the time series plot. A time series plot is a graph that shows how a measured value changes over time. The x-axis represents time, days, weeks, shifts, etc. The y-axis shows the measured value, like output, defects, or waiting time. Each point on the plot is a single measurement at a specific point in time. When you connect the points, you can visually see the direction of change, which is exactly what trend analysis is about. This makes the time series plot one of the most intuitive tools for tracking process behavior over time. Let's take a moment to reinforce the purpose of a time series plot and how it works. Purpose of a time series plot. First, it's a great tool to monitor process behavior, especially before and after a change or improvement. It helps us see if the process is truly getting better over time. Unlike control charts, time series plots can highlight gradual changes that might not trigger control limits but still indicate a shift in performance. It helps us detect trends early, so we can take action before a problem escalates. And it serves as a powerful visual communication tool, showing the history and direction of a process in a way that's easy to understand. What is a time series plot? On the x-axis, we have the time sequence. This could be days, weeks, batches, or any consistent time unit. The y-axis shows the measurement we're tracking, such as response time, defect rate, or productivity. Optionally, we can add a reference line to show a target value or specification limit, which makes it easier to compare actual performance to the goal. Altogether, the time series plot helps us connect data to process behavior and turn numbers into visual insights. Now let's go over the different types of trends we might see in a time series plot and how to interpret them. Types of trends. An upward trend means the measured values are increasing over time. This could indicate a problem growing worse, like rising defects or wait times. A downward trend shows improvement, where values are consistently decreasing, such as shorter cycle times or fewer errors. A cyclical pattern appears as regular rises and falls, often linked to things like work shifts, seasons, or weekly workload patterns. And no trend means the process is stable, with values randomly scattered around a consistent level. This is what we usually hope for in a controlled process. Example: interpretation. Let's look at a simple example. Suppose we're tracking the daily defect count. In weeks 1 and 2, the process looks stable, with defects holding steady. But in weeks 3 and 4, there's a noticeable increase in defect counts. This shift tells us we need to investigate what changed in week 3. Maybe a new machine, material, or procedure was introduced. By recognizing these trends early, we can take action before the issue becomes more serious. Let's walk through how to create a time series plot, and then we'll look at its key advantages. Creating a time series plot. In Minitab, it's very straightforward. Go to Graph greater than Time Series Plot greater than Simple. Then select your variable. This is the data you've collected over time. And click OK. That's it. In Excel, it's also simple. Use the Insert tab, then choose either a scatter plot or a line chart, and select your data, with time on the x-axis and the measurement on the y-axis. Advantages of a time series plot. It's easy to create and even easier to explain, making it ideal for team discussions and reports. It helps us detect trends, shifts, or cycles visually, so we can quickly spot when something's changing in the process. It's a powerful tool for communication, especially when sharing results with stakeholders who prefer visuals over raw data. And finally, it helps us identify when we need deeper analysis, like a root cause investigation, control chart, or hypothesis testing. So, it's often our first visual checkpoint in understanding how a process behaves over time. Let's begin by understanding some limitations of the time series plot, and then we'll transition into box plots, another useful visual tool. Limitations of time series plot. One major limitation is that it doesn't include control limits, so we can't say whether variation is within acceptable bounds. It also doesn't quantify statistical significance. You see the pattern, but not whether it's meaningful or just random variation. It can show you that something changed, but it can't tell you why. It doesn't isolate the root cause. So while it's a great first step, a time series plot is not a standalone solution. You'll usually need to follow up with deeper analysis, like control charts, hypothesis tests, or process reviews. Now, what is a box plot? A box plot is a graphical summary that helps us understand the distribution of data across different groups or categories. Each box shows the spread and center of a dataset. It displays the median, the interquartile range, IQR, the minimum and maximum, and any outliers. This makes it especially useful when comparing different groups, like different machines, shifts, or temperature settings, because it shows both variation and central tendency at a glance. So while time series plots show behavior over time, box plots help compare distributions between categories. Let's dive into the purpose of a box plot and review its key components so we know how to interpret it effectively. Purpose of a box plot. A box plot helps us compare the variation and center of data across different groups or time periods. It's especially useful when we want to see how a process behaves before and after an improvement, or when comparing shifts, machines, months, or any other category. For example, you might use a box plot to compare the turnaround time of invoices before versus after automation, or defect rates across different production lines. Key components of a box plot. The box itself shows the interquartile range, IQR. This is the middle 50% of the data. The line inside the box marks the median, which represents the center of the data. The whiskers extend to the minimum and maximum values, excluding outliers. Any dots beyond the whiskers are considered outliers, unusual values that may need investigation. The x-axis displays the groups or categories we're comparing. The y-axis represents the measurement or metric, like time, cost, or error rate. Together, this gives a compact visual summary that reveals both spread and central tendency and helps spot inconsistencies or potential problems across categories. Let's look at an example interpretation of a box plot, and then I'll walk you through how to create one in both Minitab and Excel. Example interpretation. Monthly defects. Imagine we're looking at defect counts over 3 months, January, February, and March. In January, we see a wide box with a low median. That tells us defects were generally low but highly variable. In February, the box is narrower, which means less variation, but the median is higher, indicating that while the process became more consistent, the average defect count actually rose. In March, we see a short box and a low median. This is ideal. It means defects are both low and consistent. That likely reflects a successful process improvement. This kind of visual comparison is one of the box plot's biggest strengths. It shows you how both variation and performance shift over time or between groups. Creating a box plot. In Minitab, go to Graph, greater than box plot, greater than with groups. Then select your response variable, what you're measuring, and the group variable like month, shift, or machine, and click OK. In Excel, version 2016 or newer, go to Insert Box and Whisker Chart. Then select your data that includes group labels and measurements. Box plots are fast, intuitive, and highly informative, especially when you're trying to compare multiple categories or time periods side by side. Now let's connect everything we've learned to practical Lean Six Sigma applications, specifically in the measure, analyze, and control phases. Practical uses in Lean Six Sigma. In the measure phase, we use time series plots to understand the baseline behavior of a process over time. Box plots to capture the baseline variation across groups, like shifts, departments, or weeks. In the analyze phase, time series plots help identify trends, shifts, or cycles, pointing to when something might have changed. Box plots are great for comparing variation and central tendency across different groups or process conditions. In the control phase, we continue to use both plots to visually monitor the process and confirm that improvements are sustained over time. Example case study: loan cycle time. Let's take a real-world example. A team is working to reduce the loan processing cycle time. Before improvement, the time series plot showed a gradual drift upward. The process was slowing down over time. The box plot showed a wide spread in processing times, high variation from case to case. After implementing changes, the time series plot flattened out, showing the process became stable. The box plot now had a narrower shape and a lower median, confirming both lower cycle time and reduced variation. This is a perfect example of how these tools work together to give both temporal insight and distribution insight, helping teams drive and validate improvement. Let's wrap up this section with a few key takeaways, followed by a hands-on exercise. Key takeaways. The time series plot helps us visualize trends, shifts, or patterns over time. It's great for spotting when the process might be changing. The box plot lets us compare distributions, helping us understand variation and central tendency across different groups or time periods. These two tools are complementary. Used together, they give us a more complete picture of the process, how it's behaving over time, and how consistent it is across categories. Exercise for participants. Now, let's apply what we've learned. You'll be working with a data set showing weekly defect counts over 12 weeks. Your task is to create a time series plot to see how defects are trending week by week. Create a box plot to analyze the spread and consistency of defect counts. Then, interpret what you see. Is there a clear trend over time? Do some weeks show more variation than others? Are there any outliers or shifts worth investigating? This will give you a great hands-on feel for how both tools support your analysis in real projects.